This is an introduction to the machine language we're going to be working with, and what I want to do with this is to go through each one of the instructions and to give some understanding about what these instructions mean. I have over on the left-hand side here a list of the instructions we're going to be concerning ourselves with. We have the name of each instruction. We have the template for each instruction. That is, each instruction is a 4-digit hexadecimal number. The first digit is called the opcode, and it identifies what the operation is, and that's also represented by this name here. And then the remaining 3 digits represent different kinds of operands, and what they represent are indicated by the letters we're using. Starting with a 0, if you see a 0 in the template, it means that that digit is ignored, and so generally we just set that digit to 0. So the opcode 4 will always have a 0 in the second digit position. The opcode C will always have 3 zeros. The opcode A will always have a 0 in the third digit position. Then we see the letters X and Y, and we see down here that X and Y are designating the address of a memory location. Every memory location can be represented by a 2-digit hexadecimal number, since we have 256 bytes of memory, and that requires an 8-bit address, and 8 bits is 2 hexadecimal digits. You will notice here that there's only 2 instructions that have XY in them. Those are the only 2 instructions that allow us to make reference to memory locations. All the others, we see R, we see S, we see T. Sometimes we'll see a U or UV. When you see a U or UV, that's actually indicating an actual number. So those digits represent actual numbers that are going to be used by that instruction. Otherwise, an R, an S, or a T indicates that we're referring to a register in memory. There are 16 registers, so a register can be uniquely identified by using any one of 16 digits, and that would be a single hexadecimal digit, which corresponds to a single letter then. When we use the letter R, that is a register, but it is also indicating that register will be receiving a value. When we use the letters S or T, those are registers, but they generally they're indicating registers that are providing the values that are going to be used. And so we'll bring this out as we go further in our presentation of the machine language. Over on the far right, I have a little notation here that is a brief explanation of what each of the instructions does. When you see a little r, it's indicating that the symbol after it refers to a register. If you see a little m, it indicates that what follows that is a memory location. So R for register and M for memory. And then if you don't see an R or an S, like here for example, it indicates that that's being understood as an actual number. All right, what we're going to do is I have a list of machine language instructions here, and I want to take the template pattern for each, and I want to present the explanation for it as indicated by these notations here, and then we're going to see how we can translate the actual instruction using the template into the actual meaning for that instruction. So let's go down the line here. I'm going to start off with our first instruction. And here's the way that you can use this. You will notice that the instruction 1, 2, 3, 4 corresponds to this pattern 1, R, X, Y. And so what we are saying is wherever we would see an R over here, we'll replace it with 2. When we see an X, we replace it with 3. And when we see a Y, we replace it with 4. So in this example, we could retype this as register 2, and then this symbol means receives the value of, and then we have X, so it's going to be actually memory 3, 4. So the implication of this is the load instruction. The implication of this is that we're loading the contents of memory location 34 into register 2, which just means we're copying the byte at that location in memory into the corresponding byte in the register. Let's go to our next instruction, and we'll see how that works. So here we have 2, 2, 3, 4. And again, we see R is 2, U is 3, and V is 4. So we'll rewrite this in that pattern. Register, it'll be 2 for R, is going to receive the value of 3, 4. And again, notice there's no ILM here. This is the actual number that's going to be placed into register 2. It's a hexadecimal number, so you shouldn't think of that as the number 34, but it's 3/16 and 4 ones, which means it's 48 plus 4 would be the decimal number 52. We're placing this value, this hexadecimal 34, which the binary pattern would be 0011, 0100. That pattern will be placed into register 2. The next instruction we have is instruction 3. This is a store instruction based on what we have here. Store means we're taking stuff from the CPU, particularly from a register, and we're putting it into memory. So load, we're putting it into registers, generally from memory, but store, we're taking it from the registers and we're putting it back into memory. And so using our translation process, we see that S corresponds to 2, and X corresponds to 3, and Y corresponds to 4. So writing that translation, X is 3. So memory location 3, 4 is going to be receiving the value of register 2. So we just simply replace the S with the 2, the X and Y with the 3, 4. So here you see memory is on the left-hand side and it's receiving a value from a register. Here you see memory is on the right-hand side and its values going into a register. These are the only two operations that involve the use of memory, and what this says is we can either get something from memory and put it into a register, or we can take something from a register and put it into memory. And that's all we can do with that. This next instruction shows how we can take a value that's in a register and we can actually copy it to another register. We can move it from one register to another, but actually we're just copying it. So here's the 0, and 0 is just 0. Then the S will be 2, so that'll be register 2, and the R will be 4. So here we would rewrite this as register 4 is going to receive the value that comes from register 2. The next instruction is an add instruction. This actually is adding numbers as 2's complement integers. So we'll get that equivalent result. Here we see that register R, that'll be register 2, is going to receive the value that we compute by using register S, which in this case is 3, plus register T, which in this case is register 4. So here we're saying we're going to use registers 3 and 4 and do an addition process, and when we finish we're going to put the answer into register 2. So here's just an important note. We always do what's on the right hand side of this arrow first, and then once we have that result we put it into the left hand side. One of the implications of that is that you could have a register that appears over on the right hand side, also on the left hand side. And let me just give you an example of that. Let's take this instruction. Let's say we write 5, 3, 3, 4. Then according to our pattern, that means we would have register 3, because that's the R, receives the value of register 3 plus register 4. And so we would take register 3's original value, we would add register 4 to that, and then we put the result back into register 3. We can even go one step further than that. Let's just do one more example here. And let's say we have 5, 3, 3, 3. And again, using this pattern approach, we would have register 3 is going to receive the value that we get by adding register 3 plus register 3. So we can use the same register throughout the entire process, and the result would be we would add this register to itself and the result would go back into this register. Effectively, this would then double the value that was originally in register 3, because it's 2 times register 3 going back into register 3. With the 7, it's very similar. It's just that we're using a different operation. So we'll write it this way. In this case, we say register 2 is receiving the value of register 3 or register 4. So we're doing an OR operation there instead of an ADD operation. The next one is doing an AND operation. So we would have, again, register 2 receives the value of register 3 and register 4. And then we have the next one is an exclusive OR operation. And here we have register 2 receives the value of register 3, exclusive OR register 4. In this next one, we're doing a write rotate operation. What we're saying here is register 2 is going to receive the result of taking register 2 and rotating it 4 places. So we would actually move all the bits in register 2 to the right 4 places. The right 4 bits that would go off the edge, so to speak, actually move back around to the left-hand edge, or to the left-hand end that was vacated by that rotate operation. The next one is what we call a branch operation. And in this operation, you'll see that we're going to be rewriting this so that the program counter is going to have its value changed to whatever UV is. In our example, it's 34, so the program counter will receive the number 34 if the register 2 that's indicated in the instruction has the same value as, we're always comparing it to register 0. So if these two registers, register 2 and 0, have the same value, then the program counter will become 34. If they don't have the same value, then this instruction does nothing. Let me do one more example of this type of an instruction and just show you a special case. So let's say, for example, we have B034. Then according to our pattern here, this would mean that the program counter is going to receive the value 34 if register 0 is equal to register 0. You should be able to recognize that register 0 equals itself always, and so this is an instruction that guarantees that the program counter's value would be changed to 34. Whereas in this instruction, in this version of the instruction, the program counter may become 34, but only if this is a true relationship. If it's not, then nothing will happen from that instruction. The last instruction is just very simply halt. So if we do this, then we just simply halt, and that would be the end of the program. So that concludes this introduction to the machine language. I wanted to show you how these instructions can be interpreted and how we can use the template to help us decipher what each instruction is going to do. We'll also take these effects and we will work backwards in discovering what instructions we should use if we wanted to write our own program using this machine language.